Hi everyone, in this video we are going to discuss about some basic arithmetical operation with radicals. So first we are going to talk about addition and subtraction. Now the two major misconceptions that we have, square root of a plus square root of b must be equal to square root of a plus b, and that is absolutely wrong. That is not correct. Similarly, square root of a minus square root of b is equal to square root of a minus b. That is also not correct. That is also absolutely wrong. Now why is that? Well, you can take a simple example. Let me give you a simple example. Let's suppose our a is equal to, let's say, 9, and suppose b is equal to 4. Now if you think about it, so what is square root of a? Well, square root of a would be equal to 3, and similarly square root of b would be 2. Then what would be square root of a plus square root of b? Can we write it like this? Square root of a plus square root of b, which is equal to now 3 plus 2, and that is equal to 5. Now what is the value of square root of a plus b right here? So if I simply write it like this, then that would be square root of 9 plus 4. That would be square root of 13, which is definitely less than 4, because 4 square would be 16 and 3 square is 9. So this value is definitely between 3 and 4, not even 4, right? However, square root of a plus square root of b, that came out to be 5. So then we really cannot say that these two quantities are equal, right? Now a quantity which is less than 4 and another quantity which is equal to 5, they cannot be equal, right? So that is one of the major misconceptions that we have. Well, we can call it a confusion also. It looks very tempting to write it like that, but those are not equal. And similarly, you can try the same thing with the square root of a minus square root of b also. So now we can try it right here. So if you say square root of a minus square root of b, that would be equal to what? That would be 3 minus 2, and that would be equal to 1. And then if we say square root of a minus b, that would be how much? That would be square root of 9 minus 4, that would be square root of 5, which is obviously greater than 2. So here you see we have a quantity which is 1, and then we have another quantity which is obviously greater than 2. Definitely they are not equal, right? So make this point very clear, that square root of a plus square root of b is not equal to square root of a plus b. Similarly, square root of a minus square root of b is not equal to square root of a minus b. So how can we do some addition and subtraction then? Well, let's take a couple of examples and we'll see how to manage the radicals in addition and subtraction. So here I am going to take an example. Suppose we have square root of 27 plus we have, let's say, square root of maybe 12. So can we write it like this? So square root of 27 is actually square root of 3 squared times 3, right? That would be 9 times 3, that would be 27. And similarly, square root of 12 can also be written as, this is 4 times 3, so this should be 2 squared times 3. And then each of the terms can be written like this. Whatever is the square number, it can come outside of the radical sign, and then the 3 squared will become just 3. When it comes out of the radical sign, it's going to be like this. So it would be whatever was the original power, then there would be this power for the radical because he is coming out of the radical sign, and then the standalone 3 will stay there, meaning the 3 to the power 1, it will stay there. Similarly, here again 2 to the power 2 or 2 squared, that would be written like this, because if we take it outside of the radical sign, then we have to put a power of 1/2. 1/2 is the equivalent power for a square root, and then within the square root we are going to keep the 3 there. So from here you can see that this is now 3 squared whole to the power 1/2, that would be 3, times square root of 3, plus here again 2 squared whole to the power 1/2, that would be 2, and times square root of 3. So now if you think about it, let's assume that the square root of 3 is like, let's say, x, right? Let's assume that this is x. So if we assume that square root of 3 is x, then how many x we have? Well, we have 3 times x plus 2 times x, so that would be 5 times x. So that would be actually 5 times square root of 3. So you can say 3 counts of square root of 3 and 2 counts of square root of 3, that would be total 5 counts of square root of 3, right? So that is how we do the addition. We can take another example. So suppose we have square root of 18 plus square root of 8. So let's try to simplify this. For this addition, what we have to do? Well, we'll first try to see what can come out of the radical sign, right? So let's see what we have inside the radical sign. So 18 is actually 9 times 2, so that would be 3 squared times 2. And then similarly 8 is actually 4 times 2, that is 2 squared times 2. So here we have a nice pattern here then. So 3 squared coming out of the radical sign becomes 3 times square root of 2. The 2 remains inside this 2 right here. It is staying inside the radical sign, but the 3 came out of the radical sign and it became half of the existing power. So now 3 to the power 1, which is 3 actually. And then for the second term we have 2 squared. If that comes out, it will become 2, and then the other 2 which was inside the radical, we are going to keep it there. So this will be 2 times square root of 2. So that is that 2 which stayed inside the radical. And then from here we can say, okay, so we have 3 times square root of 2 and 2 times square root of 2. So that would be total 5 times square root of 2. So let's take a couple of examples for subtraction. So suppose we have 5 times square root of 18 minus 2 times square root of 8. And if we have to do this subtraction, so we can say, okay, first term is 5 times square root of what is 18? Well, 18 is actually 9, which is 3 squared times 2. And then 2 times square root of 8 is again 2 squared times 2, that is 4 times 2, 8. So then if you think about it, we already had a 5 outside for the first term, and then when 3 squared comes out, it becomes 3. So it would be 5 times 3 times square root of 2, and minus again 2 times, when the 2 squared comes out of the radical sign, it becomes 2, and then we are going to be left with one more 2 inside the radical sign. So it will be like that. So this simplifies to 15 times square root of 2, and then minus 4 times square root of 2. So now if you think about it, if you assume that the square root of 2 is like x, right? So we have 15 times x minus 4 times x, that will become 11 times x, which is 11 times square root of 2. So that is our answer. Maybe we can take one other example. Suppose we have an example like this. So in our example, we have square root of 50 minus square root of 32. So if we simplify this, what it is going to look like? Well, the first term is actually square root of 50 would be 2 times 25, and that would be 5 squared. So that would be 5 squared times 2. That would be 25 times 2, that is 50. Minus 32 again. 32 is actually 16 times 2. So 16 would be 4 squared. So we can write it as 4 squared times 2. And then if we simplify it, it's going to look like the 5 squared coming out of the radical sign will become 5, and the 2 remains inside the radical, minus 4 squared coming out of the radical sign will become 4, and the 2 remains inside the radical. So now you see this is 5 times square root of 2 minus 4 times square root of 2. In fact, you can solve it like this. You can say, okay, let's take square root of 2 as a common factor, then we are left with 5 minus 4. You can think of it like this also. So this is becoming square root of 2 times 1, and that is actually square root of 2. Or if you think of it like this, so we have suppose 5 times x minus 4 times x right here. If we assume that this is x, then we have 5 times x minus 4 times x, that would be just 1 times x, and x is square root of 2, so it would be 1 times square root of 2, exactly what we got there, right? For multiplication and division, we are going to use the same properties of radicals that we have explained in the previous video, where we have extensively discussed about the properties of radicals. There we have taken care of the properties involving multiplication, properties involving division, so we can use the same properties there. So here maybe we can take a couple of examples for multiplication and division. So let's take our first example for multiplication. Let's say suppose we have an example like this. So suppose we have 2 times square root of 3 multiplied by 3 times square root of 2. So here whatever number is outside the radical, they can be multiplied easily. That would be 2 multiplied by 3 because they are outside the radical. So I'm going to multiply them like this. And then we also have the square root of 3 and times square root of 2 also. Right, so this is our total product, and from here we can say, okay, this is looking like 6, so that 2 times 3, that becomes 6, and then square root of 3 times square root of 2, that will become square root of 6. That's from the property of radicals. If we have square root of a times square root of b, that becomes square root of ab. So using that same property, this is the value we get. So the product of these two radicals would be 6 times square root of 6. Let's take an example for division. Suppose we have square root of 30 divided by square root of 5. Now square root of 30 would be what? Square root of 30 would be 2 times 3 times 5. 30 is actually 2 times 3 times 5, and then here we have square root of 5. So then I can write it as square root of 2 times 3 times square root of 5. I can separate the 5 from the other two factors, and then we have square root of 5 in the denominator. So from here we get that this square root of 5, this square root of 5 will cancel each other in the numerator and the denominator. So we are going to be left with square root of 2 times 3, which is 6. So our answer is square root of 6. Let's take one other example. Suppose we have an example like this. So we have square root of 24x cubed divided by square root of 6x to the power 5. So how can we simplify this? Well, let's see what happens up there. So square root of 24 is actually 2 times 2 times 2 times 3. That is the prime factorization for 24. And then we have times x times x times x. We have x cubed there. And then down below what we have? Here we have square root of 2 times 3, that is 6, and then times we have x times x times x times x times x, and then these two up there, the 2 times 2, that is 2 squared, the 2 squared can come outside, so this will become 2 times within square root, we are going to get square root of 6, and then again we have 2 x's right here, these two also can come out as a single x, so that will be times x, and then we are going to be left with one more square root of x there, and divided by, let's see what I have down below, so we are going to be left with square root of 6 over here, and then for the x, let's see how many pairs we have. Well, we have one pair and we have two pairs there, right? So then for each of the pairs we are going to get an x, and for the other pair also we get one more x outside the radical, and then within the radical we have square root of x, and that is going to be equal to, you see, the square root of 6 will cancel out each other. This one x in the numerator will cancel one of the x in the denominator. So then in our numerator we will have 2 times square root of x, and divided by, in the denominator we have x times square root of x. And then from here you can also see, in fact I could have done it in the first step itself. Again the square root of x will cancel out each other, so we are going to be left with 2 divided by x. So that is our answer. Next we are going to discuss about rationalizing radicals. Suppose we have a radical like this, 2 divided by square root of 3, and we have been asked to rationalize the denominator of this radical, right? So what do we mean by rationalization? Well, if you look at the denominator, it's an irrational number there. Square root of 3 is not a rational number, it is an irrational number, right? And we have been asked to somehow convert the denominator into a rational number. So what we need to do? Well, somehow we have to make it square root of 3 squared. Somehow you have to square it, otherwise how can it become a rational number, right? If we square it, then we are going to get 3, then yes, obviously it is going to become a rational number. Now with that, what exactly we did? Well, we multiplied by square root of 3 in the denominator. So if we have to get a square like this, essentially we are talking about something like this. Our denominator need to look like this. It needs to look like square root of 3 times square root of 3. Then only our denominator will become a rational number. Now we already had 2 in the numerator, then with 2 what we need to do? We need to multiply a square root of 3 also, because if we have a fraction like this, we can always multiply the same number in the numerator and the denominator without altering the value of the fraction. So the fraction's value is still intact, right? Now from here you see, so we have 2 times square root of 3, and then divided by, here we have square root of 3 squared, and that's pretty nice. So from here we say, okay, it is 2 times square root of 3 divided by 3. So that is actually 2/3 of square root of 3. So now you see, we have only one number in the denominator, and that is a rational number, which is the number 3, positive 3, right? So this is how we rationalize denominators. Now if we had a number like this, suppose we have something like, let's say, square root of 3 divided by 2, for example, right? I just flip it. Whatever example we had, we just flipped it, right? So from here, if we are asked to rationalize the numerator, then again I need another square root of 3 in the numerator. So what I'm going to do, I'm going to forcefully multiply square root of 3 in both the numerator and the denominator. And then what happens? We get square root of 3 squared in the numerator, because this time we are rationalizing the numerator, and then in denominator we have 2 times square root of 3. So this becomes 3 in the numerator, and then here it is 2 times square root of 3. So now you see, we really don't have any irrational number in the numerator. The numerator is looking like a rational number, and whatever we have in the denominator, that does not matter, because in this particular example we have been asked to rationalize the numerator, not the denominator. In the first example we were asked to rationalize the denominator. In the second example we have been asked to rationalize the numerator. So I showed you how to rationalize it, right? Now let's take another example. So suppose we have 1 divided by 2 plus square root of 3. Suppose this is a radical number and we have to rationalize the denominator because we already have an irrational number in the denominator, so we have been asked to rationalize the denominator. Now you see, the only way to get rid of this square root here or the radical symbol here would be if somehow we can bring it into a square form for the square root of 3. For that particular radical, if we can somehow bring it into a square form, and that can be done in one of the nice ways here. You see, if you assume that this is a plus b, right, then if we can somehow convert it into like an a squared minus b squared, then you see that if b is our square root of 3, then we can get rid of the radical sign, right? So what I'm trying to do here is that, well, a squared minus b squared is actually a plus b times a minus b, and we already have a plus b in the denominator, so I need an a minus b. That means what I need here is that I already have 2 plus square root of 3 and I need a 2 minus square root of 3. So I'm forcefully multiplying that 2 minus square root of 3 in both numerator and the denominator. And if I do that, then my original fraction value would still be intact because we are multiplying both the numerator and the denominator by the same number. So our original fraction values should be same as before, right? So then from here, what can we say? Okay, so our numerator is now 2 minus square root of 3. And then our denominator now is a plus b times a minus b, that would be a squared minus b squared, and then that can be written as 2 minus square root of 3 divided by, this would be 4 minus 3. Square root of 3 squared would be 3, so this would be 2 minus square root of 3 whole divided by 1, and that is actually 2 minus square root of 3. So after rationalizing the denominator, we see that this original fraction right here, this original fraction is actually looking like this value right here. So actually they both are equal. These two values are equal. We really have not changed the value of this fraction. We just change the look and feel of the fraction. So after rationalizing the denominator, we get that the value is 2 minus square root of 3. Next, we are going to talk about how to compare radicals. Now, comparing radicals could be tricky at times, right? So suppose if we are given an example, let's say we have 2 square root of 2 and we have, let's say, square root of 10, and we have to compare between these two numbers to find out which one is larger than the other one, right? Which one is the largest one and which one is the smallest one here, right? So what we need to do, first we need to convert them into pure radical. So what is this then? Well, this is actually, if you think about it, this is actually, so let's talk about the first one here. So now I'm going to say, okay, this first term right here is equal to, it would be square root of, if I bring the 2 inside, the 2 will go inside as a 4, and then 4 times 2, so this will be 4 times 2, and that will be square root of 8, and that would be equal to 8 to the power half, right? And similarly, if we talk about the square root of 10, here I am writing right here on the side. So suppose our square root of 10 is actually 10 to the power half. So now you see that our first number is 8 to the power half and the second number is 10 to the power half. Then obviously the second one is the larger one. So we can say, okay, now we have brought them into the same exponent. If you can somehow bring them into the same exponent, in this case exponent is 1/2, that is the exponent, right? So because our 2 times square root of 2 is actually 8 to the power half, now because we have the same exponent, and we can again write them as square root of 10 and square root of 8. So you can look at it from this aspect also, that if you somehow can bring them into the same root or same exponent, then you can compare them. So now if we compare them, you can clearly see that the term with the number 10 will be higher than the term with the number 8. So this will be greater than, the first one will be greater than the second one. So we can say, well, then this must be greater than the square root of 8. That means from here we can say, okay, then 2 times square root of 2 is definitely less than square root of 10. So the whole concept here is that we have to bring both the numbers into the same exponent. Somehow we have to convert them into the same exponent. So let's take another example. Let's suppose we have 2 times square root of 2 and the other number is, let's say, cube root of 5, for example. Now we have to compare between them, which one is larger and which one is smaller, right? So now for the first one here, so if it is 2 times square root of 2, we can write it as square root of 4 times 2, because if the 2 goes inside the radical, it goes as a square, and then this will become square root of 8, and we can write it as 8 to the power 1/2. Similarly, if you think about the cube root of 5, the cube root of 5 also can be written as 5 to the power 1/3, right? Now you see we have a situation where the base is also different and the exponent is also different. Now when you have a situation like this, again our main objective would be here to somehow bring them into the same exponent. So now if I want to make their exponent equal, we see that 3 and 2, we have 1/2 and 1/3. So if you focus on the 3 and 2, their LCM would be 6. So somehow if you can convert them into an exponent of 1/6, then we should be able to compare them, right? So now here I'm going to try and convert it into an exponent of 1/6. So if I have to do that, then what is it? This is 8 times, we can say, okay, we already have 1/2, and then if we multiply like this, 3 by 3, right? Because we can always multiply by a 1. 3 by 3 is nothing but 1. But guess what? This helps this thing to become 8 to the power 3 by 6. That means we can say, okay, this would be 8 cubed whole power 1/6, right? Similarly, let's try the same trick here for 5. So we can say, okay, this is 5 to the power 1/3, and if we multiply by 2 by 2, so this becomes 5 to the power 2 by 6. This becomes 5 squared whole to the power 1 by 6. Now you see that we have the two numbers with the same component. We have a 5 squared, so we can write this one as, so that this one can be written as 25 whole to the power 1/6, and then the first one is actually 8 cubed to the power 1/6. That would be 512 to the power 1/6. So let me somehow write it here. So maybe I can write it up here. So we can say this is actually 512 whole to the power 1/6. Now if you look at these two numbers, you see that both of their power is same. So I'm now highlighting these numbers here, number 25 and the number 512. They both have the power 1/6, right? So now you can easily make a guess that who would be the larger one. Well, in this case, obviously the larger one would be the first one. The smaller one would be the second one, because 1/6 power of 512 versus 1/6 power of 25, obviously the first one will be larger. So we can clearly say that 2 times square root of 2 is definitely greater than cube root of 5. So whenever you have to compare two radicals, always try to bring them into the same power. Somehow you try to bring them into the same exponent, and once you are able to do that, then you should be able to compare it. I hope everything made sense. Thank you for watching. See you in the next video.